Hello, everyone, and welcome to my talk, The Semaphore Architecture in a Nutshell. My name is Radosław Woźniak, and I'm one of the engineers working at the Semaphore. I'm eager to explore the technical foundation of the Semaphore with you, how it operates behind the scene, how the components interconnect, and what happens from the moment of you push the code until the build is finished. The Semaphore is an efficient CI/CD platform, yet its simple appearance masks the complex architecture consisting of over 30 microservices, various communication protocols, and a strong infrastructure that ensures smooth pipeline operations. We will break down this into the key sections, focusing on both how the semaphores run under the hood and how developers interact with it. To give you a roadmap, let's take a look at the agenda. We will begin with the overview of the semaphore architecture, what technologies we use, and how they are fit together. Then we will move into the CI/CD processing, this core flow where semaphore takes a git push and turns it into the running job. We will break this down into key components, how webhooks triggers pipeline, how jobs are orchestrated, and how results are communicated back to the users. After that, we will cover the CI/CD management, where users interact with Semaphore to configure the environments, manage projects, and control the access. Here we'll discuss how communication between services is structured, how authentication and authorization work, and how we introduce new services into the system. Now that we have a clear structure of the talk, let's start with the foundation, the semaphore architecture. The understanding this will give us the context that we need before diving into how the system operates. Semaphore is a powerful CI/CD platform designed to be both scalable and easy to use. While it may seem simple from the outside, under the hood it operates on a sophisticated distributed architecture, and every part of the system is designed for high performance, fault tolerance, and seamless automation, ensuring that developers can focus on shipping the code while Semaphore takes care of the heavy lifting. But what makes this possible? The key lies in Semaphore's core technologies, the way service communicates, and platform and infrastructure that ties everything together. Let's take a closer look. At the heart of the Semaphore architecture, there are core technologies that powers its reliability, scalability, and efficiency. Elixir is the foundation of our system, chosen for its fault tolerance, concurrency, and ability to handle high-load environments. All that is essential for CI/CD platform that processes thousands of jobs. While Elixir is a primary language, we also use Go in certain areas where it makes sense for performance and efficiency. There is also a legacy service in Ruby, but that is in the process of being rewritten in the Elixir to align with the rest of the stack. And of course, we have some HTML and JavaScript for presentation layer. Beyond the technologies themselves, communication between the services is a key to make everything run smoothly. External communication happens over the HTTP, which is how users interact with Semaphore API and UI. But internally, we rely on the gRPC, which gives us better performance and strict contract between the services. For asynchronous messages, we use Rabbit, which allows our services to handle background tasks efficiently and scales as needed without blocking the execution. All of this is built on a robust platform designed for scalability and resilience, and the Kubernetes is there in the core, ensuring that our system can scale dynamically based on the workload demands. For storage, we use Postgres as our primary database, while Redis helps speed up operations with efficient caching. And of course, as I mentioned before, the RabbitMQ plays a key role here as well, acting as the backbone for asynchronous communication. These strong architectural foundations allow the Semaphore to handle workloads efficiently. So now let's see how it comes all together. Semaphore is designed to support two primary workflows. Each plays a crucial role in how the system operates. The first is the CI/CD processing, and this is the backbone of the Semaphore. It is a main execution flow where jobs are triggered, orchestrated, and then executed, ensuring that every code change is built, tested, and deployed seamlessly. From the moment a Git push is detected, Semaphore takes over processing the event, defining the pipeline, preparing the jobs, and finally executing them on the agents. And the best way to understand the processing is to follow the code change from push to execution. And at the heart of this process are three key components that handle the events, orchestration, pipelines, and executing jobs. As you can see here, it all starts with the hooks processor, which acts as the system first checkpoint. Its job is to detect incoming events from the Git repository, validates them, and ensure they are correctly formatted and authorized before passing it further to the system. Once an event is approved, it moves to the next stage, to the pipeline processing. And here, Semaphore reads the YAML configuration, determines the sequence of execution, and orchestrates dependencies between different pipeline stages. And finally, when everything is defined, the process moves to the job processing. And this is where the system gathers all the necessary resources, assigns jobs to the available agents, and ensures smooth execution. These components work together in a structured sequence, as you can see, ensuring that every code change flows seamlessly from detection to execution. Let's go now deeper and see how it works step by step. The first step in this CI/CD execution is a hook processing, where Semaphore listens for incoming events and decides whether they should trigger a pipeline or not. And this step is crucial. It ensures that only authorized and correctly formatted webhooks moves forward, preventing unnecessary or unauthorized executions. To handle this, Semaphore relies on two dedicated services. The first one is Hook Receiver, which accepts incoming webhooks from the Git repository. Its job is to verify whatever the event is something Semaphore should process and checks its authenticity. Depending on the repository provider, it validates it through the signature of the payload, or it's checking the secret key from the headers. If everything checks out, the event is accepted and passed forward. And this is where the hook processor takes over. And this service parses the payload, converts it to our internal format. It also enriches the data with additional details from the organization and projects and other internal APIs, ensuring that all necessary context is available before moving forward. The processor hook is then stored in the database for traceability and make it easy to debug and audit later if needed. With the webhook validated and processed, Semaphore moves on the next stage, the pipeline processing, and this is where the system interprets the pipeline definition and orchestrates the execution. And here, with webhook successfully processed, Semaphore now knows that the pipeline needs to be executed. But before the job can run, the job needs to be structured correctly. Dependencies must be managed. The execution must follow the intended sequence, and this is where the pipeline processing comes into the play. At the heart of this stage, there is a service called Plumber, which responsibility is to define and orchestrate all the pipelines. And Plumber doesn't execute the job itself. It focuses on interpreting the YAML configuration file from the repository, figure out what steps needs to be performed, and ensuring that everything happens in the correct order. If pipeline has multiple stages with dependencies, Plumber ensures that they run in the right sequence, preventing jobs from executing too early or out of the sync. Once the pipeline structure is finalized, plumber coordinates execution, passing the job definition along to the next stage in the system. Think of a plumber as a conductor of the orchestra. It doesn't play the instrument itself, but it makes sure every section comes in at the right time. Once everything is prepared, it hangs off the execution to the next system in the pipeline. And for those who are interested how plumbers work under the hood, there will be a deep dive talk by Damian, where he will go into more details about how it drives Semaphore CI/CD process. The pipeline is now fully defined, but it's still just a plan. The next step is turning this job definition into the real execution, and this is where the jobs processing comes in. The service responsible for this part is called Zebra, and it plays a crucial role in making sure that jobs run smoothly and efficiently. Before sending the job to the agent, Zebra, also using the internal APIs, collect all necessary details. It fetches secrets, pull credentials for the artifacts, and gather other repository informations. And these steps ensures that when the job starts, it has everything it needs to succeed. Once all the required data are in place, Zebra assigns the job to available agents. From this point, the agent takes over and runs the workload. But Zebra doesn't just hand it off and forgets about the job. It actively tracks the state and moves through different stages. This ensures that jobs are efficiently dispatched and executed in the right order. When the job completes, Zebra updates its final state. But if something goes wrong, like a job exceeds its allowed execution time, Zebra forcefully terminates it and marks it as times outs to prevent it from blocking other jobs in the queue. This structured approach allows Semaphore to reliably track job execution, making it easier to debug issues, retry jobs when necessary, and maintain the clear execution history. Now, while the Zebra is responsible from preparing and tracking jobs, the actual execution happens on the agents. And if you are curious about how agents work under the hood, Lucas will cover this in one of the next talks. And yeah, now that all jobs have been executed and the pipelines are reached its final states, there is one last crucial step, and this is like notifying external systems about the outcomes. And this ensures that users stay informed and the version control system accurately reflects the latest build status. As soon as pipeline completes, whatever its success file or is like cancelled, the system generates the completion event, and Plumber publish this event as a rabbit message, allowing other services to pick it up and process notifications accordingly. One of the key service responsible for notifications is the notification service, of course. Depending on how the system is configured, it can send real-time updates to the Slack or to the webhooks. Another important piece of external communication is updating the status of the commits in version control system. And this is handled by another service called GitHub Notifier, and which this service ensures that repositories receive the latest build results. And this completes the standard pipeline lifecycle, but not every execution starts with a new Git commit. Let's take a look at the other ways pipelines can be triggered in Semaphore. So beside commits, user can also start a workflow by a rerun, or can start only a debug job without starting the whole workflow. Each of these enters the system in a slightly different point, but all of those communications go through the API layer. So when the workflow is rerun, the process doesn't start from scratch from processor. Instead, it begins directly in the Plumber, in the pipeline processing system, And this means that pipeline configuration is reloaded, the jobs are redefined, and execution flows the same structured flow as for new commits. Once completed, notifications are sent just like in the standard pipeline run. On the other hand, when a user starts a debug job, they are not triggering any pipelines, just a specific job. So because of this, the processing bypass the hook processor and pipeline processor altogether and start directly in the Zebra, the job processing system. Zebra gathers the necessary information, prepares the job, and dispatch it on the agent, ensuring that it runs in isolated environment. This flexibility allows Semaphore to handle various use cases efficiently, whatever a developer wants to rerun an entire pipeline or just investigate a single job. Okay, so we explored the entire CI/CD process flow from the moment of commit is pushed to when the job is executed and results are reported to various systems. While it may seem simple on the surface, under the hood, multiple services work together to ensure that every step from detecting a change to running a job and delivering notifications happens smoothly, reliably, and also at the scale. Okay, so far we focused on one part of the system, how Semaphore runs jobs, but running jobs is not only it's not like the only part of the picture. Teams also needs to have a tools to configure the environment, to control the access, and integrate the workflows. And that's where the CI management comes into the play. While processing is all about running jobs efficiently, management is what gives user control over the environment. This is where developers and teams configure projects, manage secrets, and set up notifications, shaping the Semaphore to their needs. In these sections, we will start with an overview of how users interact with Semaphore through the UI and API. From there, we will dive into authentication and authorization, breaking down how access control works to keep the system secure. I will also show you how internal services communicates with HTTP handling external requests and gRPC used for internal communication, ensuring efficient and strict service contracts. Finally, we will go over how new services are introduced into the Semaphore, starting with a profile definition and ensuring a smooth and maintainable integration. Okay, so let's take a closer look at how Semaphore services interact behind the scene. So since user interact with Semaphore through the UI and API, all these communications happen over HTTP. However, internally, the requests follow a structured layered approach designed for security, maintainability, and scalability. We are using there the gRPC. Frontend and API services handling incoming requests, but they don't have access to the database. Instead, they communicate with dedicated backend services, which holds the business logic for managing projects, secrets, notifications, and other key system components. These backend services are responsible for enforcing rules, processing data, and ensuring each part of the system operates independently without creating a bottlenecks. This separation of concerns allows Semaphore to remain secure, modular, and flexible. It ensures that new features can be introduced without disrupting existing functionality, while maintaining a clear structure for how data flows through the system. And one of the most important aspects here in this CI/CD management flow is ensuring that the only right users have access to the right resources. Semaphore achieved this by separating authentication from authorization, allowing fine-tuned control over who can interact with different parts of the system. Before a request even reaches the frontend or API service, authentication is handled by the out service, and this service verifies the user identity and inject the user ID headers to the request, ensuring that all downstream services can trust the authenticated user. To manage user sessions securely and seamlessly, we integrate with external identity providers. Semaphore relies on a keycloak, the robust and widely adopted open source identity and access management system. Once authenticated, the request moves forward, but access is not automatically granted. This is where authorizations comes in, enforced by the Airbag service. Frontend and API services call Airbag to check whatever the authenticated user has necessary permissions to perform the given action. After the verification, all internal communications is trusted, and meaning that services assume the request has already been authenticated and authorized. By keeping authentication centralized and authorization granular, Semaphore ensures security without compromising performance. And this layered approach allows for precise access control while maintaining system efficiency. Okay, so now that we've seen how services interact with Semaphore, within the Semaphore, let's look how we introduce new services while maintaining consistency and reliability. So as Semaphore continues to evolve, we constantly introduce new services to expand its capabilities. But adding a new service isn't just about writing the code, it's about ensuring that it fits seamlessly into the existing system without causing disruptions. To maintain consistency, all internal communications happen via gRPC, which enforces a clear structure for how services interacts. And the first and the most important step when adding a new service is to define the service contract. And this is done by writing a protofile, which serves as a blueprint for how the services will communicate. It specifies the RPC methods, request and response structures, and expected data types, making sure that a clear agreement between services before any implementation begins. Once the protofile is in place, both sides of the communications needs to generate the necessary definition files, reinforcing a strict contract between them. From this point, the service is fully integrated and can be called just like any other existing component. By following this structured approach, we ensure that every service speaks the same language, minimizing the integration issues and allowing Semaphore to scale smoothly without breaking dependencies. So, Semaphore is a highly distributed system, carefully structured to separate CI/CD processing, where jobs are executed, from CI/CD management, where users configure and control the environment. In CI/CD processing, we saw how a Git push triggers a structured pipeline with hooks, pipeline orchestration, and job execution working together to ensure builds run efficiently. On the management side, we explore how Semaphore allows users to configure environments with UI and API. A well-defined communication structure ensures that security and performance with external requests using HTTP and internal services communicates over gRPC. We also look at how authentication and authorization worked with Keycloak managing sessions, out handling identity verification, and Airbag enforcing permissions to ensure a secure and scalable access control system. Finally, we saw how new services are introduced into the Semaphore. By first defining the protocol contract, we ensure a reliable and structured integration process, keeping the system extensible and maintainable as it grows. Now that you have a better understanding of the Semaphore architectures and internals, I encourage you to get involved and contribute. Semaphore is an open source project, and your insights, feedback, and contribution can help us improve even further. Thank you for watching this.
Hello everyone, today I'm excited to share a small part of our journey of launching the community edition of Semaphore. Whether you're thinking about open sourcing your own product or you're just curious about what happens behind the scenes, I'll do my best to give you a product manager's perspective on what it was and what it still is like open sourcing the product, the challenges, the surprises, and of course the lessons we learned along the way. But before we jump in, take a moment to check out our GitHub repository and give it a star. At these early stages, it definitely means a lot to us. It's Semaphore.io on GitHub. So, yeah, when you get the chance, check it out, add that star. And yeah, let's move in. So, we're going to break this talk into two main parts. First, we are going to talk a bit about product challenges, well, some of them at least, and what we learned about the key differences between our cloud and community edition. And we're also going to touch a bit upon operational challenges and how we're trying to shift to this building in public approach and what we're doing to get the developers and end users directly involved into shaping the product. But before we get into all that, maybe let's start with a big question that every product manager asks first, and that is why? Why are we open sourcing Semaphore in the first place? Well, from product perspective, our goal is very simple. We want to make Semaphore available to larger audience. We already have a solid base of monthly active users, but over time we realized something important, and that's that there are so many talented developers who just cannot use our product because it's a cloud-based solution and that's not always available to everyone. Um, or they're using a different tech stack. So we decided to open source Semaphore and do whatever we can to make it accessible to a wider group. And with that decision came a clear opportunity, and that is a more inclusive product equals a better Semaphore, or at least we hope that will be the case. So, long story short, the reason from product side why we're doing making this step is to get a wider audience, more eyes on our product, and hopefully get a lot more feedback on it, which should result in a better Semaphore and experience for all the users overall. However, as soon as we made that call, one thing became clear, and that's that our onboarding experience needs a complete overhaul. Now, getting onboarded to a cloud app versus an open source app is a lot like traveling with your parents versus traveling solo in your 20s. When you're with your parents, everything is planned, flights are booked, hotels reserved, meals sorted, and that's the cloud experience. It's got built-in support and structure. But when you're on your own, it's a whole different game. You got more freedom, less commitment, but also way less guidance, and that's usually the open source experience from my point of view. You're in control, but you have to figure a lot of things on yourself. So this shift made us realize that we need to rethink how we guide and support users through their open source journey, and that's why onboarding users to open source app can be way more challenging. There's just no support team to help smooth out product and UX issues. There's no safety net. Users are on their own. So in order to improve our onboarding in product, we defined these key success factors, and we realized that these are the things that you want to pay attention to. First of all, is simple installation. Our users come from all kinds of backgrounds, and we wanted to make sure that Semaphore is easy to install and works smoothly across various tech stacks. In-app onboarding without support team to act as a crutch. We have to have a product that itself does the heavy lifting in this area. And great documentation is crucial for any open source project, really. I mean, we always treated the docs as a part of the product, but in this particular case, they are essential. They are a difference between users sticking around or bouncing, in my opinion. So by focusing on these, we aim to improve the whole onboarding experience and make it self-sufficient. Now, one challenge that we had is how to test it, and some lessons that we learned here is that if you're thinking about redesigning onboarding in your own app, first thing you have to do is make sure you eliminate domain knowledge. No one in your team can truly experience onboarding like a first time user. They just know too much. To get a real insight, you need external testers, ideally from different backgrounds, who can provide fresh and unbiased feedback. Second thing is screen recordings are absolutely essential. Bug reports, tickets, those are all helpful, but nothing beats watching real users struggle in real time. Screen recordings give you a full picture and make it easier to spot bottlenecks and friction points. But you also don't want to forget the quantitative goals and feedback loops. So you need to define and track measurable goals. You can optimize onboarding forever. This is one product area that can always be improved, but eventually you need to know when to stop. And setting a clear, measurable goals like success rate, time to first success, definitely help in this area. So the key thing to remember is that onboarding isn't a one-time fix. It's an ongoing process, and on our end, we've just started the journey in making the Semaphore Community Edition more accessible. We're excited really to test on how well the changes that we made so far are working. But no matter what the results are, we know that the road ahead of us is still long. You know, so one thing to note if you're considering open source is when it comes to onboarding, it's a whole different game between cloud and open source product. Yeah. So now on, let's switch gears a bit and dive into operational challenges. But before we get into that, I feel like we need to align first on what open source really means for us as a company. Uh, the common mistake that people are making, in my opinion, is treating open source as a business model. It's not a business model. In reality, open source is a collaborative process. It's not about making money directly, at least not in traditional sense. I mean, over the years, we've gained incredible value from working closely with the customers. The direct feedback that we get during those interactions is amazing. And for a dev tool product like ours, the dynamic is a bit different. Our users are developers, and as a product manager, that's a dream come true, because you have end users that have a deep understanding on the whole process. So that's why we wanted to take it even further, and we didn't want to just engage with a subset of our users. We wanted to bring all end users into the fold and involve them directly into our design process, and ideally collaborate with them at every single stage of our product development, right? So if you're thinking about open sourcing your product, here are some of the benefits that we personally hope to achieve. We would, by making this move, we would like to get an early feedback. Oh, let's do this. Yeah, we want to get early feedback. By involving end users and developers in design process, we hope to shift left our product design and catch design flaws earlier, uh, and improve our product with real world insights. We're also hoping for faster innovation. Public projects need to stay active to succeed. So we plan to use Community Edition platform to keep focusing on smaller product improvements and deliver more frequent updates. Something that we've been slightly neglecting on the cloud version in favor of larger features. And we are also hoping that we'll get better feature prioritization by making our roadmap public and democratizing the whole process. We hope to align more closely with what users actually need and deliver the features with greater accuracy. So, with these benefits in mind, the question is what goals are we setting to make sure we actually achieve all these benefits? And from an operational perspective, at least, our goal is simple. For a start, we want to make it easy for users to contribute to Semaphore's development. So this means in practical terms, clear contribution guides, well-documented code, and a beginner-friendly setup so that new contributors can get started quickly, etc., etc. I mean, the key challenges and the things to pay attention to, something that we are still tackling, is number one, rethinking the roadmap ownership. It's very important to find the right balance between commercial goals and community input so we can build a product that works for everyone. And I'll explain a bit the way we're trying to solve this. Supporting contributors is a pretty important item, making sure contributing to Semaphore is a frictionless experience by providing clear docs, well-scoped issues, and open, welcoming community. And the last thing is building in public, like overall, shifting our entire team's mindset to embrace this sort of transparency where collaboration and open discussions happen in public and the things that shape our product decisions happen in public. So we got a lot to figure out, but that's all part of the journey. I don't know if you're a Power Ranger fan, but to me, the whole process feels a lot like building a Megazord. So it's like bringing together these different components to create something much greater than the sum of its parts. And the key tools that we are currently using to make open collaboration easier is number one, treating contributor experience like product experience. So we already treat documentation as part of the product, and we're applying the same mindset to contributor experience. So as the first step, we have set an ongoing project dedicated to improving the whole developer experience for those that wish to contribute to Semaphore. It's in early stages, but we do plan to iterate in close future. Second thing is allocating dedicated resources to Community Edition. We want to ensure that the Community Edition never gets sidelined. So we've set up a system where it gets its own track and fixed amount of engineering hours every month. It can a minimal amount of engineering hours every month. It can go beyond what we've set. So it's not just an afterthought for us. And in terms of embracing public development, we are slowly but surely moving from private team chats in Slack to public discussions in Discord. We want to fully open our build process. So we're also recording and sharing our feature design sessions. You can actually check it out on YouTube on Semaphore Backstage channel. So anyone can follow or even contribute to our decision-making process. In fact, some of these sessions are already open to public, and then you can join them. Which, speaking of, if you're excited to join us on this journey, here's how you can get involved. Number one is joining our Discord. Connect with us, join the Discord. All the updates that we have regarding Community Edition will be happening there. There's a small number of groups there already, but we tend to increase that as we shift from Slack. Sign up for special interest groups. Right now we have 3 smaller groups, but we plan to open more soon. This is a great way to dive deeper into specific topics and collaborate directly with our team of like-minded developers during the design stages of the product. Number 3 is share your ideas and feedback. We want to hear from all of you. That's why we're doing this in the first place. So drop your thoughts in GitHub discussions and issues. Your insights will help shape Semaphore's future. And ideally, become a contributor. Contribute to the project. If you or someone on your team would like to contribute, let us know. Reach out to us either on Discord or through GitHub. We'll do our best to support and guide you every step of the way. We're excited to build this thing together and to make the open source Semaphore a success. Once again, thank you for joining me on this session. Remember to visit our repo and hit the star on GitHub, and happy building.
Hello, everyone. My name is Amir, and I'm engineer here at Semaphore. I will share with you our journey of improving the Semaphore API. In the next 10 minutes or so, we'll try to briefly go over our current API infrastructure state, our vision of improved API with a more cohesive, maintainable, and developer-friendly experience, hopefully not just for us, but also for our users. Some guidelines that we established based on experience, and finally, I'll try to give some pointers if you're interested in contributing or giving some feedback. I'll be honest with you and say that our current API isn't exactly where we would like it to be. Over the years, we accumulated multiple different approaches of serving our API, each posing its own set of challenges. Part of the API is defined with gRPC and protocol buffer. It uses a gRPC reverse proxy that translates between RESTful HTTP API and gRPC. The gRPC calls are implemented across multiple services, or gRPC APIs are implemented across multiple services. And then each service needs to maintain both internal and public APIs, which is not ideal. And then also we had issues with translation between HTTP and gRPC that didn't always work as we expected it to. So it proved a bit more cumbersome than what we would like it. Some of our services also expose their own HTTP APIs. This wasn't ideal because maintenance becomes increasingly complex as we add more services. Our third and most promising approach is the one we chose to improve further, and it's a dedicated service acting as HTTP server, and this service then translates incoming requests into our internal API calls with the full control of the translation. The same ones that we are using the internal API, the same one that we use for inter-service communication. What we love about this approach is that we have a centralized implementation for security features, a single point for implementing response formatting, single point for validating requests, and it's generally easier to maintain and update. Taking these lessons to heart, we are unifying the API under a single cohesive approach, and the goal being to provide a consistent, predictable experience, making it easier to integrate with Semaphore. Hopefully also making it easier for other developers to extend our API and keep the documentation up to date. With these goals in mind, we landed on resource-oriented design. We would like to have communication collocated with code so we don't forget to update it, as it often happens. So the clear obvious for this is Open API, and we would like to enrich the resource representations to make the API more flexible. More about that in a bit. I've chosen only a few things to speak about from our core principles and best practices. This is not all of it. The response format, the resource-oriented design for us meant objects containing kind, metadata, and spec. So the kind helps in identifying the nature of the resource. Is it a secret, a project, or the deployment target? The metadata field contains all the non-functional information that helps identify and manage the resource. And the spec field contains the functional configuration or the desired state of the resource. This is where the actual content of the resource is defined. The rich resource representation for us started as objects instead of IDs, and this is what we have currently created by, for example, instead of just providing the user ID, we will provide the object that qualifies the object type as user, and then we have the ID there as well. So this allows us to extend the API in the future with providing the backwards compatibility as well. Resources that are scoped to some parent resource, usually a project, usually also can be identified by name. That name might be used in multiple projects, and then nesting under project resource becomes necessary. So this ensures that resources, we prevent any ambiguity in cases where the same resource name might exist in more than one project. So also Semaphore's API supports some custom methods for performing actions that extend beyond basic CRUD operations. These methods allow the API to handle resource-specific operations like starting, stopping a workflow, for example, or any other needed actions. These actions don't follow the standardized resource object pattern, but contain only required information for that particular action. For these, we are using the resource path for identification, and we will try to provide actionable error messages if something fails. These actionable error messages we would like to have for everything, but let's say that we would like to especially have them for actions on the resources. I mentioned that co-located documentation is important for us, and the obvious choice was OpenAPI spec, as we want to heavily use it for documenting the API behavior. In the first efforts of specifying the API with OpenAPI specification, we stumbled into issues with mutually exclusive required parameters and decided that instead of trying to fit a square peg into a round hole, as they say, the goal is to change the API so it can be gracefully described by the spec and also rendered with commonly used tools. And that's why we are also excited about OpenAPI 4.0 talk that we've seen. I'll try to just be very brief here for the project structure. We have internal clients there. These are the gRPC clients that make the internal service calls between different components of the system. Each client typically implements mapping from request, so from the specification into internal API requests, and also the other way around. Responses are formatted from internal API into the specified API. Yeah, so into the specified API response format. In the project, you also see handlers. They are each one file per endpoint, so they are separate and easier to reason about. Each handler defines OpenAPI operation, and that allows for standardized data validation and validation errors. They each also define authorization permissions that are required for the operation. Also, they restrict or modify the behavior based on feature flags and sometimes prefetch or combine data that is needed to perform the internal API request. Hopefully, I've at least tingled your interest and you would like to see more and give some feedback or contribute in some way. We would be really happy if you did do that, and there are many ways to make the API better, and if you are interested, you can head over to this URL. We will provide it in the description or somewhere, and we'll be very happy to hear from you. Maybe we can go into the actual GitHub, and maybe I can give you a brief introduction. Let me see. Okay. So you would head over to Semaphore repository, and in the public API v2, we have a Elixir project. For those familiar with Elixir, they will know where to find the code in the lib, and then in the public API we have the main project. Here we define the routes that we have in the API. That's pretty self-explanatory, and yeah, except the trick is that we are not using Phoenix. So for the Open API specification to work properly, you also need to define the operations here in the API spec file. As you can see here, we have Another thing is handlers. So let's see an example of one handler. Let's go to projects and maybe create. So the handler always plugs this plug for casting and validating the request. This takes the request from HTTP into an object that you defined in the specification. We usually have audit logging there plugged as well. So we log the operations that are happening. We have the authorization plug that I mentioned and the permissions needed for it. If you go deeper, you can see the list of these possible permissions that are that we have documented internally, but we will share with you if you are willing to contribute what and how to handle those. And in the end, we have metrics and the actual plug that's the handler of this request. So we try to provide, this maybe not the best example, but we try to provide some documentation here as well. There are schemas which we can go and look later on. And basically the create handler is pretty simple. We just take the parameters that were cast by the Open API plug and forward it to the internal client, which then, let's see, the internal client. We have an internal client first. Let's maybe see here. This is the main module of the internal client. It defines all the operations that are there. And then this is, we are delegating the form request and process response. Those are the main ones to separate modules to keep this one clean and small. And let's see what project hub client request formatter holds. So we said create project. So we are forming a request for creating. We are using internal API, and let's see, project. We are basically building the internal API request here. And yeah, that's about it. All you need to know to get started contributing. We will also have some discussions open here on the repo, and we probably will have some RFCs opened for the public API as well. So see you in the pull requests and discussions on the Semaphore.io Semaphore repo. Bye.
Hello, everyone. My name is Lucas. I am one of the engineers here at Semaphore, and today I'm going to be talking to you a little bit about self-hosted agents. We'll look at a few of the details of how things work under the hood, and also discuss a little bit some of the challenges we had to face while developing it. So that's it. Let's get started. So I think it would be helpful for us to start by looking at Semaphore from a distance. And if we do that, we can notice two very distinct parts of Semaphore, the control plane and the agent pool. So the control plane is the brains of the operation, right? It does everything. It orchestrates pipelines, it handles secrets, it receives hooks from the Git providers, has workers to control everything, right? All the logic for Semaphore live in the control plane. And on the other side, we have the agent pool, which is just a group of agents. And the agent is where the Semaphore job actually run. So when you add your commands in the Semaphore YAML, they will eventually end up in the agent, and the agent will execute them. Now, since these two parts are quite different, they can run in very different ways. For example, if you're using SaaS with no self-hosted agents, all of these components live inside of our SaaS infrastructure. Now, if you use SaaS with self-hosted agents, you can also use these agents inside of your infrastructure while using the control plane and maybe even some of the cloud agents that we have running on our infrastructure. And with this community and enterprise editions, what you get is both of these parts run inside of your infrastructure. So you have full control over everything. So let's start diving a little bit more on the details of how these two parts talk to each other. First thing we need to understand here is, how does the control plane know about the agents? And to understand that, we look at the process we like to call agent registration, which is the first thing that the agent do when it starts. So when you start a new agent, the agent will send a registration request to the control plane. Now, that request needs to be authenticated, so it needs this agent type registration token, which is a token that you get when you create a new agent type. When you go to the UI, you create a new agent type, and the UI will give you this agent type for you to use when starting the agents. Now, when the control plane receives this request, it will run a few checks, and if everything is okay, the new agent will get a new unique agent access token. And from now on, all the requests from the agent will use this access token that is unique to it. So we mentioned that the control plane runs some checks when it receives a new registration request from an agent. And one of those checks happens to make sure that the number of agents that are running at the same time does not go over the limit. We call this limit the organization quota. Now, in this example, the organization quota is 4. So the first 4 agents register just fine, and then the 5th agent is rejected. Now, how does the control plane enforce this? And you might think, well, this is quite simple, right? You just count the number of agents that are currently running. And if the new agent pushes that over the limit, you just reject. And well, yes, that is the answer. We're going to dive in a little bit more into the control plane to understand the common pattern that we use across the entire Semaphore code base to make sure that this number of agents is always below the quota. So let's look a little bit more on the control plane. Up to this point, we have been looking at it as this cloud intelligent piece, but we really didn't look inside of it much. So let's zoom in a little bit more on it. If we zoom in, we're going to see that the control plane is actually a bunch of different services running together and talking to each other, just like a regular microservice architecture. So each service is responsible for its own part of the system, and they all work as a whole to make Semaphore work as expected. What we want here, though, is to look specifically on the service that handles all this communication with the agents, which is the self-hosted hub service. Now, let's zoom in a little bit more again. Here, we can see that the self-hosted hub service is also composed of multiple instances of itself that are running at the same time. This is, again, very common in microservice architectures because this makes it very easy for us to scale up and down and meet the demand and the load that comes from the agent and from the service. But with this architecture, we have one issue. So let's go back to the problem of enforcing the quota. So for every request that the control plane gets, it has to do two things to check the quota, right? The first thing is to count the number of agents running. And then if that number is below the quota, we add the new agent to the pool. The problem here, though, is that these operations are not atomic. So they're not executed as a single unit. So if a bunch of requests for multiple agents come at the same time, we could end up with a situation like this. Here we have a quota of 4, and we currently have 3 agents running. And we have 2 agents here that are sending registration requests at the same time. We can see that one of those requests comes to one of the instances of self-hosted hub, and the other goes to the other one. And since checking the quota and register the agent are not executed atomically, we can't guarantee that one's going to execute, they are going to execute together for the same request, right? So here we can see that actually both checks for quota happen before any of the agents are registered, so they both succeed. And we eventually end up with one agent above the quota, which is a mistake. And how do we fix this? Well, we need to combine those 2 operations into one single atomic operation. And the way you force that is by using a lock. In our case, if we only had one instance of the self-hosted hub service running, we could use an in-memory lock and call it a day. But here we have multiple instances running, so we can't really do that. And we need to use a distributed lock. In our specific case, we use a Postgres advisory lock. Since the quota is applied on the organization level, we use the organization ID for the lock. So all the requests for the same organization end up using the same lock, which ensure that all of them are executed one after the other atomically. So going back to our example from before, again, our quota of 4 and 3 agents running, we can see that the checking quota and the register operations are grouped together and executed one after the other. So the first one succeeds and the second one doesn't, because it would push the number of agents over the limit. Okay, let's move on a little bit. So now the agent is registered, but what does it do next? So once the agent starts and successfully register with the control plane, it enters the waiting for job state. Now it will remain in this state until a new job is sent to it from the control plane, in which case it's gonna go to the running job state. And again, it will remain on that state until that job is finished. And once the job is finished, it will move to a finished job state. Once it's here, it's gonna send an update to the control plane that the job is finished. And then it's either gonna disconnect, depending on your configuration, or it's gonna go back to the waiting for job state. Now, the agent doesn't transition between these states by itself. The one who actually controls these transitions is the control plane, more specifically the self-hosted hub service. And it does that through what we call the sync protocol. And the sync protocol is just a series of requests, one after the other, separated by an interval that is repeated until the agent disconnects. For example, here's what the sync protocol looks for an ephemeral agent. Now, an ephemeral agent is one that starts, registers itself, and runs a single job only. And after that job finishes, it disconnects. And here we can see how exactly that happens. So it starts by sending a waiting for job state. There's no real job in the queue yet, so the control plane tells it to wait a little bit. And after it sends it again, it receives a command to run the job. And it starts running the job until the job finishes and the agent is told to shut down. Now, here's what the sync protocol looks for a reusable agent. Note that it looks very similar to the ephemeral agent, with the exception that once the agent reports that it finishes the job, the control plane tells it to go back to the waiting for job state. So between one request and the other, there's an interval. How big is that interval? Well, initially we had a fixed interval that was configured on the agent side, but as the number of agents registered started to grow, we realized that there were a few improvements that we could make to more effectively control all this load that comes from the agents. First thing that we realized was that the intervals didn't have to be always the same, right? So we could make them conditional on the agent state. For example, if an agent is waiting for a job, we want that agent to react to a new job entering the queue as quick as possible, right? So in that case, it makes sense for us to use a smaller interval so that that agent starts running that job that is in the queue faster. Another thing we noticed was that we could move this interval logic to the control plane instead of keeping it in the agent. That would give us a little bit more control over certain situations. For example, if the self-hosted hub was having trouble keeping up with all the requests that come from the agents, it could start applying some back pressure to the agents and increase that interval so it has a little bit of a breathing room to recover. Another example here is if we ever want to change this interval logic, having it in the control plane is better because once the new version of the control plane is released, all the agents will start reacting to this change immediately. Instead of, if that was on the agent side, we would need to release a new agent version with this change, wait for everyone to upgrade to the new version, and only then we would see a change in the behavior. Okay, now we understand a little bit better the overall communication between the agent and the control plane. But what about the job execution? We didn't really see how that works, right? We saw the agent goes into this running job state, but how does the user on the job page running the job sees all these job updates that come from the agent? So that is only possible because the agent sends job logs to the control plane while the job is running. So let's look at a little bit of the details for this. Again, here to understand this, we need to zoom in again on the control plane because it's a different service that handles all these job logs updates. And we call that service Log Hub. So the agent sends a bunch of requests to Log Hub while the job is running. Each one of these requests contains a batch of logs, and it is followed by another request containing a more recent batch of logs. And this whole process continues until the job finishes, in which case the agent flushes all the logs that it has for the job that it is running. Okay, let's look more closely at data flow for these job logs while the job is running and also after it finishes. So while the job is running, the agent is sending all these requests to the Log Hub API. The Log Hub API, while the job is running, is appending them to this Redis server. After the job is done, the agent will send a request to the self-hosted hub through the sync protocol to indicate that it finished the job. At that point, the self-hosted hub will send an event to the Log Hub archivator, which will fetch all the logs for that job in the Redis server, collect them, archive them, and send them to a bucket, which is the final destination for all the job logs. Now, while this is happening, a user using the job page could hit the Log Hub API to fetch the logs for that job, and the Log Hub API will go to Redis and return the logs to the user. Or if the job is done, it will go to the bucket and return to the user. And that is how the job logs go from the agent to the user's browser. Now, one thing we need to do here is to make sure that the Log Hub APIs are not being overused by some job generating a lot of output, because that could cause the Log Hub APIs to become irresponsible to all the other jobs running at that time. And since we can't control really the amount of logs that a job generates, we need to add some protection on the API. So we do that by making the API reject requests after the logs go over a certain size. So here the agent has sent a bunch of requests and has filled all the space that it has for that job. And then after another request that pushes that over the limit, the Log Hub API will return a response saying that it should stop sending logs because it will start rejecting all of those requests now. But what if I really need those huge logs? Maybe I'm debugging something and I need all the logs that I can get. So what then? Do I just lose all those extra logs? Well, no. In this case, the agent will keep collecting the logs in its disk, and then after the job, you can configure it to send all those huge logs to the control plane via a job artifact. Okay, so we talked a lot about the communication between the control plane and the agent. Now let's focus a little bit on the agent. And first things first, the agent is a Golang application that has been open source since 2018. And we compiled that application to several different operating systems and architectures. So you can run that agent pretty much everywhere. You just need to grab the agent binary and a VM, and you're good to go. However, things can get a little bit more complicated than running a single agent, right? For example, you might want a new clean and pristine machine for every job that you run. So that way, one job doesn't interfere with the other jobs that are executing. And if you really need that, then you first need to create one machine with the agent running inside of it, wait for that agent to receive a job, run the job, and finish the job. And after the job is finished, you need to shut down the agent and terminate the VM. And in its place, you need to create a new VM and start this whole process all over again. Another thing you might really want is for your agents to scale up depending on the number of jobs that you have in your queue. For example, if new jobs are created and added to the queue, you want your agent fleet to also increase in size and create new agents to handle all those new jobs that enter the queue. And we also have the other side of this queue, right? The same way that you want the number of agents to increase when the job queue increases, you also want the number of agents to go down when the job queue decreases. So once the job starts finishing and no more jobs are put in the queue, you want the agents to start disconnecting and the machines to be terminated, right? You don't want to overspend on your VMs. Now, all these challenges are handled differently depending on the environment that you are. For example, in AWS, you have a different set of tools than you have in Kubernetes. In AWS, you need to figure out how to build these AMIs that are going to be running these agents, how to configure the outscaling groups so you can make your agent pool bigger or smaller depending on the size of your job queue. You're going to need to figure out how to configure the scripts that start the agent once the instance is created, and also how to terminate the instance once the agent is shut down, so you can rotate the agents for every job. Another thing you need to do is configure IAM roles to give permissions to the agent and also to the job that the agent is running to manage resources in your environment. And finally, you want to be able to troubleshoot issues. So you need to be pushing logs and metrics to some place that you can monitor. Now, all these tools that we used for AWS don't really exist in Kubernetes. So you need to handle all those problems of agent rotation and scaling them up and down with different tools like Kubernetes deployments or custom controllers or horizontal pod autoscalers. But here we can help you, since all of these issues and challenges have already been addressed by a few additional applications that we developed and maintain that act as this supporting cast to help us handle these challenges for agent management. For example, for AWS, we have this CDK application for deploying the stack, which works for these three Linux, macOS, and Windows operating systems, and all those problems are already solved there. And for Kubernetes, we have this custom controller that already does the same thing and solves all those problems, but for the Kubernetes environment. And this is where we need to wrap things up. Now, we want to continue to make Semaphore easy to run wherever you need to run it, and hopefully now we can do that with the support of the open source community. Thanks for joining me today, and goodbye.
Welcome. My name is Rick van Hoef, and today I'll be telling you the story of how we started self-hosting Semaphore CI to get faster CI pipelines. As I said, I'm Rick van Hoef. I live in Utrecht, a city in the Netherlands. I've studied computing science at the university of the same city, and currently I work as a DevOps engineer at a company called Channable, and I'm at the developer experience team, which is a team that focuses on CI/CD and developer tooling. Channable is a company that's also based in Utrecht, building a software as a service, an e-commerce solution that connects web shops to marketplaces, price comparison websites, and advertisement platforms. And just to give a little bit of a sense of scale, we export 200 billion items every single day. Our software stack is based on React, Rust, Haskell, and Python. React for the front end, Rust for some of the performance critical parts, Haskell for the rule compilation engine, and Python for lots of the domain specific code. And we use Nix as a build toolchain. Nix is a bit of the odd one out on this slide, but it's very relevant to how our CI pipelines work and for the trick that we use to speed up our CI pipelines. And that's why I will talk a little bit more about what Nix is. So Nix is a reproducible build toolchain, and reproducibility means that wherever you perform the build and whenever you perform the build, the output, the exact bits will be the same. And having exactly the same bits in a development environment, in CI and in production means also that certain classes of bugs are better reproducible. And Nix does this without any container involvement. So this isn't just a Docker replacement, but it's a different way of sealing off your builds and making them reproducible. And a way that feels more natural, more native to Linux. In order for Nix to create reproducible builds, you will have to pin dependencies for your build all the way down to the C compiler. So let's take example project. It needs Click as a library. It needs Python as an interpreter. But besides the versions of Click and Python that we need to specify, we would also need to specify the version of the C compiler that this version of Python would be built with. And this is just an example. Actual dependency chains will look a lot bigger than this, of course. And if you would build this specific project, you would end up with a few entries in the Nix store. And the Nix store is a content-addressed store that you can find on your machine in /nix/store. And each of the entries in this store corresponds to some dependency or some specific build of some specific package. And they are identified by a hash. And this hash is based on the build inputs. So this means all of the dependencies plus the source code. And because this hash is based on the input, this means that it can be calculated before you start the build. And this gives a nice caching property. Nix can, instead of start building the project or the dependency, it can also query a cache for this hash with this hash and ask the cache, hey, does this already exist? Do you already have this built? And if that is the case, you can just download it from the cache. And again, here reproducibility pops up. Because you know that the builds are exactly reproducible between different machines, you know that the build that resides in the cache will be exactly the same as that you would have built locally. A big part of the Nix ecosystem is Nix packages, which is a cache with pre-built packages, 100,000 plus and going, and it includes, for example, C compilers and Python and all sorts of Python dependencies, and also for other programming languages. And this means you don't actually have to build and specify all of the dependencies, but you can get pre-built versions of these dependencies from Nix packages directly. And for things that we build ourselves, so these are non-open source projects, things that we only use within Channable, we can push those to Cachex, which is sort of similar to Nix packages, but to cache your own custom packages. And also part of the Nix ecosystem, for those in the know, is NixOS, which is an OS that is built around the Nix package manager. And we do not use this as Channable, we use the Nix package manager and build toolchain on top of Ubuntu. To go back to the original topic of this presentation, we want to optimize CI. We want to make CI pipelines faster, and there's two main reasons why we want to do this. The first is to increase developer velocity, and this means that we want developers to get feedback about their work quicker. So if they make a PR, CI is started, and we want them to get feedback from CI on that PR as fast as possible. So less waiting time for the CI pipeline. And the second reason to be optimizing CI is to cut costs. So if your CI pipeline takes less time, in general, you would also need less compute, and this means it will be cheaper. So if you want to optimize your CI, there's two main directions you can think of. One is parallelization, and the other is adding more processing power. And if you're trying to parallelize your CI pipelines, this means you want to split up a job into multiple smaller jobs that all do part of the work. And this only works until a certain point, because every task has inherent fixed costs. And if you split the task in three, this means you will pay this fixed cost 3 times. And so at some point, this doesn't scale very well anymore. And I'll come back in the next slide about what these fixed costs exactly are. Another solution you can go for to improve CI times is adding more processing power. And this also works till a certain point. So there's some IO bound work that you maybe need to do in a CI pipeline. This will not speed up, but your CPU bound work will, of course, speed up with adding more processors or more cores. So where does the CI time actually go? Well, for us, the CI pipelines were taking a lot of time to do a few specific things. Populating the Nix store, so this means restoring from cache this whole Nix store, and then at the end of the pipeline also pushing the Nix store back to cache. Also, we spent a lot of time on Git LFS. And Git LFS is the Git large file system, which is an extension to Git that makes it possible, as the name implies, to work with large files. And another thing that we were spending quite some time on is some setup steps, for example, installing Nix and Cachex in each of the job runners. And since most of these things are slow because of cache, there's a few directions that we thought of. We could try to cache less. So maybe we want to put less files in Git LFS, or try to cut down our dependency chain for Nix. This is a hard problem. Over time, each project gathers more and more dependencies, and to cut dependencies always is very time-consuming and costs a lot of developer effort. But the thing that we can do is move each of the caches closer to the jobs. So we started looking into how our caching infrastructure looked. And in the before situation, there's Nix packages. In front of that is Cachex. In front of that is the Semaphore cache, and there we put a full copy of the Nix store. And then we restore the whole Nix store at the start of each job run to the local job runner. And at the end of each of the job runs, we store that Nix store back to the Semaphore cache. and we push specific dependencies that we're interested in to cache 6. And we figured we could do a little bit better than this. So we still have Nix packages and cache 6. But instead of using the Semaphore cache, we use an in-network Nix cache. And because this cache knows how Nix works, we can now cache and restore individual dependencies instead of the whole Nix store at once. And instead of using and having a Nix store in each job, we have a Nix store on the host. And so this means we have a host machine that runs this multiple CI jobs, and it has a full copy of the Nix store. And from there, we push to the in-network Nix cache into cache 6. So our architecture looks like this. We have this big fast server with lots of fast storage. And on this storage, we have the Nix store. And on the host, we launch a bunch of containers. And each of these containers runs a single CI job. And inside of each of these containers, we mount read-only the Nix store. So each of the containers has the same view of the Nix store. And they can write to the Nix store via the Nix daemon. So they talk to the Nix daemon, which will then build things and add it to the Nix store. So in this way, we share the builds and the dependencies between all of the containers. And this works very well because of reproducibility. So work that would have been done in 2 containers can now be done shared in the Nix daemon. And if one container already has done the work, it's already in a Nix store and the next container can just pick it up from there. There's also a few other optimizations that we did once we had those self-hosted setup. For example, sharing the Git checkouts. So instead of every time cloning a repository from GitHub, we get the latest copy from GitHub on a timer, like say every hour on the host. Then we mount this checkout as read-only in each of the CI containers. And then we have a custom checkout script that does a checkout with reference to this read-only copy. And this is way quicker than a full clone from GitHub, especially when Git LFS is involved, because now all these large files are already mounted inside of the container. Other things that we also did is move lots of the setup steps from the CI job description to the container image. So this is, for example, installing Nix, cache 6, and Redis. And the results are there. So for one of our bigger projects, the runtime went down from 24 minutes to around 4 minutes. This is really the best case, of course. And this repository was relying heavily on Git LFS. But for a different repository with also very high developer traffic, our runtime went from about 9 to 10 minutes to about 4 to 5 minutes. And you can see that there's huge differences in the wins per specific job. So some jobs are more compute intensive, do a lot of actual work, and those didn't speed up that much. But some of the jobs were mainly just restoring a Nix store, then doing a few things, and then storing the Nix store back. These jobs have sped up considerably. In general, we saw a 2x speed up for an average CI pipeline, and we also saw some unexpected side effects. So one of these side effects is that we could parallelize more of the CI pipelines. Because we have now this lower fixed cost, we can split up jobs in even more smaller jobs, and with that help the total runtime of a pipeline. And we also saw that developers started to do more releases. And this doesn't mean that developers got 50% more productive, as this graph could imply, but it does mean that our developers did smaller releases, and smaller releases are better viewable, easier to test, and easier to roll back. So this is still a big win in our book. Of course, all of this work didn't go without challenges. So one of the things that cost us quite some time when we started up is converting each of the CI pipelines to our self-hosted setup, because there was quite some differences between the hosted and the self-hosted setup. We also have a still unsolved problem of the Nix builds. So these Nix builds happen on the host in the Nix daemon, and the problem here is that there's no per container resource limits on the Nix builds. And this means that if an adversary would control one of the CI containers, they will be able to exhaust all of the resources on the host, or at least all of the resources we allocated for Nix builds for all of the containers from a single container. And we also were struggling, especially at the start, with co-location. So originally we ran this whole setup on a cloud instance, but we quickly realized that the costs of this were higher than we were paying before. So we figured that we needed to build our own physical server, which we did, and we placed it in a rack in the office. We quickly realized that our office isn't really equipped to have servers there that blast out a lot of heat. So we had to look for a co-location location to host our server in. We have not converted all of our repositories and all of our pipelines to the self-hosted setup. The benefits really depend on the projects, so it didn't really help for projects that are not using Nix extensively, for example. Also, we have left behind all our open source projects on the hosted CI because of the aforementioned reason of the resource limits of the Nix builds. So there's a few things that we've learned along the way. And the main thing that we want you to bring home is that you want to keep your caches as close to the actual work as possible. So instead of having the cache network hop away, try to get your cache on the local machine. And if you're not using Nix, which is likely, you could perhaps have a shared Docker daemon on the host. Also, a thing that we really didn't expect to run into is the law of induced demand. So while we were doing this, we realized that if you're measuring your progress, you have to do so immediately, because as soon as developers start getting used to the faster CI pipelines, the performance decreases will be used up by new requirements, new tests that are run, new workflows that require more usage of CI. And this is fine. This is actually a good thing. We get more work done. We run more tests, but it really screws up your measuring. If you measure a month after the changes instead of just a day after the changes, you will see that your measurements don't just measure the changes that you did, but also the extra demand that was added. And you have to keep this in mind for measuring. So that was it. Thanks all for your attention. I'll be still in the Discord to do some Q&A. And if I don't see you there, have a nice day.